Let us consider some other cases of inexistence of equilibrium. Huh? Look at this case. Here there is a point which represents initial endowments, trace the budget line, and suppose that for consumer 1 you have a usual structure of indifference curves, and there is this optimal point. But suppose that for consumer 2 the indifference curve has this form. What happens? Note that in this case you have two optimal points. They belong to the same indifference curve, of course, and it is the highest indifference curve which touches the budget constraint of the second subject. However, in this case, what property of preferences is not verified? Clearly, convexity. Let us rotate the usual way the graphic for subject 2. The situation is the following, where you have an indifference curve like this. Clearly, since this is a point which gives to a subject an higher level of utility, if you consider these 2 points which both give an higher level of utility, however, at some point on the segment which unites x prime h and x second h, like 2 in this case, sorry, 2. 2. I'm not preferred, I'm not over the indifference curve, but they are below, and not above the indifference curve, but x2 is below. So in this case, you remember from the first part of the course, preferences are not convex. Clearly, in this case, there is not equilibrium. No? You can change prices, but when the difference curve has this form, note that the point d1 of p is intermediate between the optimal points of the second subject. But it does not coincide neither with the first nor the second. So there is not equilibrium by lack of convexity. This is very important. Convexity is, generally speaking, essential. Convexity of preferences is essential in order to prove the existence of equilibrium. If you remove convexity, generally speaking, equilibrium may not exist. Another case of inexistence of equilibrium. This is omega, as before. Here there is the common budget line. Suppose that the preferences of a second subject are the usual form. So this is the optimal point of a second subject. But note, this is important, that the preferences of a first subject as not the usual form. In particular, they are not monotone. Let us trace the preferences of a first subject in a separate graph. Suppose that there is a so-called bliss point, a beatitude point. The different curves has this form. In other terms, there is an unconstrained maximum of utility for our consumer. With respect to this point, no preferred alternative exists, and clearly preferences are not monotone. Is it clear? Let us draw this particular structure on difference curve in this graphic. This is the indifference curve which passes by the initial endowment. There is another indifference curve, and suppose that here there is the bliss point. The point of beatitude, the unconstrained maximum. Is it clear that this point is the demanded point? D1 of P for every P with no negative components is exactly equal to X bar 1. While the optimal point of subject 2 is as usual on the budget line. While the optimal point of consumer 1 is below the budget line. In other terms, he does not use all his initial wealth. A part of this wealth remains unemployed. Clearly, in this case, there is not equilibrium. This is the optimal point of subject 2. This is the optimal point of subject 1. Let us represent the situation of subject 1 directly. This is omega, and note the optimal point is below the budget line. In this case, in which monotonicity lacks, there is no equilibrium. Not only monotonicity lacks, but also local non-saturation, another well-known property of preferences, lacks in this case. So, these are all cases of inexistence of equilibrium. It is relatively easy to show that equilibrium may not exist. The difficult problem, as I told before, is to prove the existence of equilibrium by means of all the properties that in these examples were absent. Monotonicity, convexity, and so on. This is the difficulty of proving the existence of equilibrium, of general equilibrium. Finally, let us suppose for a moment that an equilibrium exists. Nothing assures us that equilibrium is unique. It's very easy to show that it is possible, the multiplicity of equilibrium is possible. Let us trace the final Edgeworth box. Here there is the initial endowment. Trace any budget line like this and suppose that here there is coincidence between the optimal points. Now let us consider this other price system. Nothing It is possible, it is possible that also in this point beta, on the alternative budget line, there is coincidence of our two optimal points. In this case, you have simply multiplicity of equilibrium. There is not only one equilibrium, but many. Theoretically, also infinite equilibrium. If you reintroduce the offer curves, this can be explained by observing that these offer curves may intersecate many times. This is the offer curve of subject 1. This is the offer curve of subject 2. Note that there are, in this case, 3 intersection points. But do you remember, an equilibrium is also an intersection point between the offer curves of our two subjects, but for the point which represent initial nodes. So, in this case, there are 3 equilibrium points. A situation more complicated than these, in which there were only 2 equilibrium points. However, multiplicity of equilibria is very, very frequent. It is sufficient to introduce some not very standard utility function, and you obtain immediately multiple equilibria. In order to avoid multiple equilibria, you must suppose that preferences verify very, very strong properties, which we shall study afterwards. Well, this is the problem of the existence of equilibrium in the simplest case. But it is important that in this simplified context it is possible also to define the concept of efficiency according to the original definition by Pareto.